What if scientists could build a telescope the size of the entire Earth without actually building one? It sounds impossible, but a recent quantum physics experiment suggests it might actually be possible, and if it works, it could completely change how we observe the universe. But to understand how scientists might pull this off, we need to start with a simple problem. Astronomers want to see extremely small details in space, distant planets, the edges of black holes, the structure of galaxies billions of light years away. But the amount of detail a telescope can see depends on one simple thing: its size. The larger the telescope, the finer the details it can resolve. Think of it like looking through a tiny hole in a wall versus looking through a massive window. The larger the opening, the more information you can collect. That's why astronomers build enormous telescopes. Some observatories are the size of buildings. Others use giant radio dishes that stretch across entire valleys. But even the largest telescopes ever built have limits. Because if scientists truly wanted to see the smallest details in the universe, they would need telescopes thousands of kilometers wide, and obviously, that's impossible to build. So scientists came up with a clever trick. Instead of building one enormous telescope, they connect many smaller telescopes together. When multiple telescopes observe the same object at the same time, their signals can be combined. And when the signals are combined correctly, those telescopes behave like a single telescope as large as the distance between them. This technique is called interferometry, and it's incredibly powerful. In fact, interferometry helped scientists capture the first-ever image of a black hole. Telescopes around the world observed the same region of space at exactly the same time. Their data was combined, and together they formed a virtual telescope nearly the size of Earth. But this technique has a serious limitation, and solving that limitation is where quantum physics enters the story. The problem with interferometry is that the signals from distant telescopes become extremely difficult to combine. Light arriving at each telescope must be synchronized with extraordinary precision. Even tiny timing errors can destroy the signal. And as telescopes are placed farther and farther apart, the challenge becomes harder and harder. Eventually, the signals become too weak to combine reliably, which means even the most powerful telescope networks still have a practical limit, unless scientists find another way to connect those signals. And this is where one of the strangest ideas in physics becomes useful. The idea is called quantum entanglement. It's one of the most mysterious phenomena ever discovered. When two particles become entangled, their properties become linked together in a very unusual way. No matter how far apart those particles move, their states remain connected. If you measure one particle, the other immediately reflects that change, even if they are separated by enormous distances. Albert Einstein famously disliked this idea. He called it spooky action at a distance. But over the past several decades, experiment after experiment has confirmed that entanglement is real, and scientists have learned how to control it. They've used entanglement to build early quantum computers. They've used it to create ultra-secure communication systems. And now researchers are discovering that entanglement can also help combine extremely weak light signals. And that discovery could completely change how telescope networks operate. In a recent experiment, scientists created devices called entangled quantum memories. These devices can store and manipulate quantum information. Researchers placed these systems in separate locations. When extremely faint light signals arrived at each location, the entangled memories allowed scientists to combine the signals in a completely new way. Normally, signals this weak would disappear into background noise, but the quantum system allowed researchers to recover more information from those signals. In effect, entanglement allowed distant detectors to behave like parts of a single coordinated instrument, which means telescopes could potentially be placed much farther apart than before, thousands of kilometers apart, and still function together as one system. In theory, this could produce a telescope with the resolving power of something the size of our planet, an Earth-sized telescope. And that's where things start to get truly exciting. If this technology continues to improve, it could unlock entirely new ways of studying the universe. Astronomers might be able to directly image distant planets orbiting other stars. We could study the regions around black holes with unprecedented clarity. We might even analyze the atmospheres of distant Earth-like worlds and search for signs of life. But the implications go far beyond astronomy. Quantum sensing technologies could transform many areas of science. They could create navigation systems far more precise than GPS. They could detect subtle gravitational changes beneath Earth's surface. They could even help scientists search for entirely new physical phenomena, all because of a strange connection between two tiny particles. Particles that behave in ways that challenge our everyday understanding of reality. For more than a century, quantum mechanics has forced scientists to rethink how the universe works. But discoveries like this show that quantum physics is not just a strange theory, it's becoming a powerful scientific tool. A tool that could allow us to observe the universe with a level of clarity we once thought impossible. And the next great telescope might not be a giant structure built on a mountaintop. It might be a network of quantum-linked instruments spread across the planet, working together to reveal the deepest secrets of the cosmos. And if scientists succeed, the universe we see in the future may look very different from the one we see today.